Welcome back. This is part 4 of Crystal Clear Electronics 2, Chapter 20. In this video, we'll use our example program to measure the power consumption of the microcontroller in different operating states. During the experiment, we will go through a cyclic menu and test at which clock frequency and which energy mode the controller consumes the most power.
To calculate the power consumption, we need to measure the current of the microcontroller. For a standard panel, such as the black panel in the written curriculum, this is more complicated than you might think. With the help of this connector, which has one of the power lines disconnected, we can connect the multimeter in series with the current flow and easily measure the total current consumption of the panel. However, this is not enough for us, as we are interested in the power consumption of the microcontroller. Therefore, we need to measure the base consumption of the panel so that we can compare it later. In the case of the black panel used in the written curriculum, the base consumption is made up of the current of the power indicating LEDs for the 3.3 and 5 volts power supply, current of the controller in reset state, various leakage currents, power supply losses, and the consumption of the 5 volts supply voltage measurement circuit found on the panel. The consumption of all other devices and peripherals will only be added to this when they are initialized and used. The power consumption of the controller's environment can be easily determined, for example, by setting it to standby mode, since only a few powered registers are added to the peripheral's power consumption on the order of a few microamperes. The resulting data is therefore a good reference for subsequent calculations. Later, it will be sufficient to subtract the value calculated here from the results obtained in the different measurement cases to obtain a good approximation of the controller's standalone power consumption.
When measuring, make sure that the board is only powered via the multimeter. For example, the ST-Link programmer for the Chinese region supplies 3.3 volts, so if it is connected, the measurement will be distorted. The version intended for the global market does not feed the microcontroller via the 3.3 volts pin. It only monitors voltage, which also introduces distortion into the measurement, but that is negligible.
To calculate the power, we also need the value of the supply voltage, which can be easily measured with a multimeter, taking care that the rotary switch and the measuring wire are not in the current measuring position.
We have to pay attention to a lot of details when using the black panel.
Yes, it's easier with Nucleo. This is why we use this type in the videos instead of the black panel. The microcontroller on the panel is powered via the jumper marked JP5. You can easily measure the current of the microcontroller by disconnecting the jumper and connecting the multimeter in current measurement mode. For this, we use this wire, one end of which fits on the pin header connector and the other end has a banana plug. On the panel, the microcontroller operates from a 3.3 volts supply voltage, but you can also measure the exact voltage of the 3.3 volts power trace to check the value.
Our assembly on the breadboard only contains a push button and a display at the moment.
The example program works and used like this. After reset, the program starts in run mode. Press the push button to move between the menu items, the names of which are shown on the OLED display. After selecting a menu item, a short countdown will activate the mode described by the selected menu item. The display is then switched off. To step to the next menu item, you have to press the button, except for the standby mode, because in that case, the microcontroller is woken by the RTC wake-up timer after 5 seconds. The settings that can be selected from the menu are shown in the figure. We have the opportunity to enter the run and sleep modes at different clock frequencies, and to enter standby and stop modes. The menu item for the VBAT mode is not displayed and measured, as the controller's current consumption in that mode is too low to measure accurately. Let's try out the program we have already uploaded to the Nucleo. At the first menu item, we will enter run mode with a clock speed of 25 MHz. Balázs, please power the panel. Here, we can see the chapter's title. Then we enter the run mode, which will be activated after the countdown. Then we can read from the multimeter after a short setup process that, as I see it, it is approaching 13.96 milliamps. Balázs, please press the button. This will take us to the 50 MHz mode. It counts down again. And that's roughly 19.9 milliamps of consumption.
Similarly, you can measure the power consumption in other modes. We have already done this, and the results for the run modes are drawn on the graph.
Let's take a closer look. From our measurement, it's clear that the choice of the clock speed does make a difference. As we increase the clock speed, the current consumption is increased. In this table, you can see the values so far, plus the values measured in sleep, standby, and stop modes. The measurements confirm what we said in the previous videos. You can see that standby mode has the lowest consumption, followed by stop mode. Then comes the sleep mode, where power consumption was measured at 25 MHz and at 168 MHz clock rate. In sleep mode, only the processor's clock is turned off, the peripherals remain active, and continue to consume power. The measurement also shows higher power consumption at 168 MHz.
As you make these measurements at home, you will get slightly different consumption values. This should not be surprising, as the actual power consumption depends on many things, such as the ambient temperature and thus the temperature of the microcontroller core. As a verification, we also check the relevant part of the datasheet before recording and confirm that our measurements match the typical values. The datasheet also gives a few milliampere difference for different temperatures.
Finally, an interesting thing to point out is that if you look at the power consumption in standby mode, you can see only 3 microamps, which is 3 to 4 orders of magnitude lower than the other modes. So if you have the opportunity to use this, for example in a battery-powered device, you can gain lots of uptime for your device. Anyway, this 3 microampere consumption is not going to change much at other temperatures either.
After examining the data, let's move on to another topic. In many development areas, there is a strong focus on minimizing the energy consumption of their devices, thus also stretching their uptime. This will also increase the lifetime of each device, as for example a battery power source will go through fewer charge and discharge cycles, and thus suffer less degradation over time.
As an example, let's discuss some areas where these aspects are important. Wearable devices represent an interesting and complex area of application. As the name of this grouping suggests, we include battery-powered products here. Examples include watches, motion trackers or smart bracelets, and devices that monitor various health metrics. Some examples of this are smart thermometers, ECGs, blood oxygen, and blood glucose monitors. There are development tools that take the burden of hardware design, miniaturization, and encapsulation off our shoulders. Once the idea is born, it can be a huge help to start experimenting and gaining experience on a reliable hardware platform, especially when example code is readily available. Such an open source platform is Hexiware. A specific requirement for equipment used in agriculture is that it must operate under extreme conditions such as extreme temperature, humidity, and particulate matter. The components of the circuit and their enclosure must be chosen to suit these conditions, ensuring adequate sealing. An imperfectly sealed enclosure can easily be penetrated by dust and water vapor. Even a sealed enclosure can accumulate dust, as the temperature difference between day and night also causes a change in air pressure. If the seals are not airtight, this can cause the enclosure to breathe in dusty air. A good example of an agricultural data logger is a probe installed in a field. As they are generally battery-powered, it's important to make them as energy efficient as possible, but at the same time, we also need a way to read out the data, in other words, to ensure long-range communication. For this, long-range modules have become increasingly popular in recent years. It can be an interesting fact that ST is also present on the market with a very low power module.
During the curriculum, we have used the term IoT quite often. It means Internet of Things. These are devices that can connect to the internet via Wi-Fi or mobile networks. One common use of the IoT is home automation. I'm sure you've already seen some of these in action, or maybe even use a few at home.
For sure. Minimizing the power consumption of the software, and therefore of the individual microcontrollers, is also an important factor in such devices. This is because most of the system components are in continuous operation, so reducing the average power consumption over a long period of operation already results in significant savings.
This brings us to the end of the chapter. We hope we've shown you a lot of useful things in these videos and that you will join us in the upcoming chapters. You can find the example program shown in the videos on crystalclearelectronics2.eu under the 20th chapter. If you enjoyed the video, give us a like, and if you are curious about a new chapter coming out or want to know more about the series, subscribe or follow our Facebook page where you can see the latest news.
Thank you for your attention, and don't forget to put your mobiles into sleep mode. Bye bye.
Bye!